So contingency tables are really important because it's a way of comparing two variables. And one of the questions that came up in the survey was, how can we look at more than one variable at a time? It wasn't, exactly that. It was words to that effect. What if we wanted to tackle like 7 or 8 different variables? Like how would we handle this? So that's something to keep in mind, that there are strategies for these sorts of things, and it usually involves some sort of tabular approach, right? So the probability of one event occurring, given that another has already occurred, is represented by this formula. This is known as conditional probability. It's an if-then condition. So when we, in one of the videos, we talked about Venn diagrams. And in those Venn diagrams, we focused specifically on the cases involving and or, which led into the addition rule and the multiplication rule. Now we're getting into the conditionals, which makes probability infinitely more challenging. Okay, so this vertical line represents given. All right, so it's a given that A has already occurred. So in real terms, or real language, I guess, this is really saying find the probability of getting B, obtaining B, having B successes, whatever it is, but find the probability of B knowing or given that A has occurred. All right, so that's what all that means. It's like, okay, knowing that A's already happened, what's the probability of getting B? Right, we focused on that a little bit when we talked about the cards. It's find the probability of getting a king and an ace. You didn't replace the cards. The first card was selected. You didn't replace it before you withdrew the second card. And because of that, the probability of getting an ace was impacted by the fact that you already got a king, or vice versa. All right. But now what we're looking at is real data. Data has been collected. You have this example here. It's a little outdated. It only goes up to fall of 2019. So I need a little reminder to update this. I'll take that as a typo if anybody's looking for typo bonus credit. Right, again, just while I'm talking about policy here, anytime you notice a mistake in the packet, grammar, spelling, or even something that I point out in class, all you have to do is send me an email with the page number or the location of where the mistake is and what the mistake is. And on a first come, first served basis, I give you a bonus point for each time you do that. I got a student in my other class, in my calc class, that has like 24 bonus points already. Like I said before with the discussion post, unfortunately, I make a lot of mistakes when it comes to grammar and spelling and things like that. So this individual is really cashing in. It's an opportunity. Take advantage of it. All right. So this really, I can update this as recently as fall 2020. But for now, it's only through fall of 2019. This is real information, though. Right? And I love including this because, one, at least it's an attempt at transparency on my end. I don't fear the knowledge of performance in my classes. If people aren't doing well, I want to know. If people are doing great, I want to know. And I want to get to the bottom of why things are going the way they are. And I can tell you that when I first started putting this example in there, I think I did it around 2005. There's only like 3 years of data in there. The responses, the results for the computations that we're about to perform told a completely different story than what they do now. Part of it has to do with what's called the law of large numbers. And that is that if you increase the number of trials, you're going to get closer and closer to the true probability. So if I could actually teach statistics infinitely many times, no, not infinitely many, because this is a finite math situation. What I'd be dealing with, like for a large number of trials, is hopefully the data distributing itself into its most accurate form. Right? Now, these are the possible grades that you can get by taking a college class, a credit-bearing class here at WCC. And these were the outcomes from that 17-ish year period. So you see here that 90 male students got A's and 157 female students got A's. All right, so hey, anybody looking at this at first glance might say, well, sorry guys, you picked the wrong gender. Like it's one of those things, like it's a simplistic look at it where you just say, well, clearly he shows favoritism towards the female. Well, really? I don't know, because you look at those D's, 13 D's for the females and 4 D's for the males. You can draw, if we're going to choose one data point, the grade, a single grade, you can look at this and say, well, a lot more D's for the females than the males. Yeah, he's showing favoritism towards the males, because D's a bad grade. We want that to be as low as possible. And you go back to the F's and say, back to the female. It's kind of like a horse race where it's like, and they're off out of the gate. The females are taking the lead, followed closely by the males, and it's getting tighter down to the finish line. And at the end, you have 59 males getting F's and 37 females getting F's. And one of my favorite things to say in a stat class is that statistics as a course asks more questions than it answers. All right, this data table has told us nothing without us diving into some computations associated with it. Because any schmo can look at this and draw some kind of conclusion. It's not going to necessarily be a good one. I'll tell you, whether it's at the high school or at the college, I got people that I work with, their administrative levels, their teachers, everybody in between, students. They think that you just put up a table and a graph and point to a number and say, well, see here, now clearly we can conclude that. I'm like, we haven't concluded anything. All we have here are counts. Now, what does this mean about the larger population? How does this project out to, like I said, the large number of trials? So this is 17 years worth of data. What if I planned on teaching for 50 years? What's it going to look like at the end of that? Do I want to necessarily have to have taught the 50 years in order to draw that conclusion? Probably not. I want to know before then, because it's the horse out of the barn kind of thing. Like if I'm doing something the wrong way, I want to know now so that I don't screw it up over the next 33 years. Right? But can I also assume that the proportional balance is going to remain the same? Is it going to roughly be a 50-50 split on the B pluses forever? Or is it a race to the true proportion? I don't know yet. All right, so we start getting into some probability analysis, and then we get into inference testing. All right, but for now, we're looking at a conditional probability, which says, for the first example, find the probability of passing based solely on the fact that you're female. I oversimplified that. This is, the language here, again, that vertical line just means given. Given that the individual that was selected was female. All right, so we have a formula. Probability of B given A, that's this guy up here. Probability of B given A is equal to probability of A and B divided by the probability of A. All right, what that translates to for this problem is the probability of passing and being a female divided by the probability of being a female. Now, this is going to lead us to a shortcut for being able to handle this kind of question. But for now, we want to actually see what, how it's going to shake out. All right. Now, remember the notation for and is that symbol, that little upside down U. That also means intersection. All right. So the and, I used the wrong tool here. And is also known as the intersection. Now, when you're dealing with multiple variables, in this case, we have variables related to grades and gender. To draw a Venn diagram that's going to account for all of these things all in one shot, it would be pretty monstrous, right? So we want to stay away from that. But what we can actually do, the term intersection, we talked about the Venn diagrams, it was two circles that intersected. Well, how about a row that intersects with a column, right? So passing and being female. So now it's not really a row for passing because it's a collection of rows. That would be all of these, anything that's not an F. This is passing. All right, so let me just highlight all that. That's all of this information. Now, some people might find it to be somewhat debatable as to whether or not a D is passing. It's technically a passing grade, but it's not a desirable passing grade. And some people would say, well, no duh, because like the A is the desirable one, the most desirable, and then after that, we got less and less degree of desire associated with the grade. That's really not what I'm getting at. I'm talking about the credit bearingness of these things. So if you get a passing grade, you at really most any college, you're awarded credit for that course. If you take a course over after having already passed that course, both the weights of both grades stay on your transcript on your GPA, right? But if you fail a class, you haven't successfully completed it. If you take it again and get a new grade, that new grade with, the F still shows up in the transcript, but it doesn't get factored into your GPA. So what a lot of people look at is a D as being a failing grade because they say, well, I got to take the course over anyway. So I want to be able to transfer it. But, it's still a bad grade. That's a different conversation. Technically, it's considered passing, so that's what we go by. All right, so that's the set of individuals who are passing. Now I want the intersection of that with the set of individuals that are female. All right, so that's this column here. Got for autocorrect. All right, so that's this set of individuals. The overlap in a very Venn diagram sort of way would be any individual that's both passing and female. So that's going to be this group here. I kind of wanted that to be an ellipse, but that's sort of what I'm up against. All right. So, what's that? So it's these values, long story short. So I need the sum of those values, but you could also look at it and say, well, do I really need the sum of them? Because I could just eliminate the folks who didn't pass. So that would be everyone out of the 365 that aren't out of this group of 37 individuals. So I could say 365 minus 37, there's 328 out of 653 that correspond to passing and being female, right? So that's out of the grand total, right? Then I would just divide that by the probability of being female in general. Now, we have a total of 365 females. out of 653 people overall. We don't do a whole heck of a lot of algebra in this class, but this is one of the algebraic skills that can kind of be helpful. And that is to say, if you have a complex fraction, so a fraction over another fraction, where the denominators are the same, they cancel out. They would cancel out if you did the keep, change, flip operation. But ultimately, this becomes 328 over 365. Right? That being said, if you didn't know that, that's okay. Just type it in. You get that decimal, but you can see the little fraction icon next to it tells us that a fraction is available, a fraction conversion is available. So you get 328 over 365 that way, right? So that's one way that we can actually look at it. That's the formulaic approach. But another way to do it would be to actually go literally based off of what the language of the problem is really suggesting. So this is saying, given that we're dealing only with the females, right? So we want to know the probability of getting a passing grade. So if you kind of look at this as saying, so knowing that the individual selected was a female, so that's a given fact. What's the probability of passing? And I'm really only looking at this group of individuals and the people from that subset, or the subset of people from that group that passed. My drawing tool didn't work there. Kind of. Best I can do on short notice. Anyway, so this is really kind of the shortcut I was alluding to, where you'd say, all right, so from the individuals, because that just looks terrible, from the individuals in question, which would be the females, right? So just focusing on the females, what is the probability of passing? So that would be 1, 2, 3, 4, 5, 6 different groups. Add them up. That gets you your 328 out of the total available, which is 365. And you could just kind of jump right to it without using the formula. But I don't think it would be a reasonable thing for me to just go to the shortcut without talking about why the formula works the way it does. All right. But now you have a formula, like, well, don't mind if I do. So from the group of males, which is this category here, all these folks, right? So it's a given that we're only looking at the males. Now I want to know what the probability is of failing. So all I would do is count or identify the number of F's within that subset, which is 59, and divide it by the total of males that are available. In this case, I'll get another highlight color in here. This one, 288. It kind of cuts out a little bit of the fluff, right? But there's pros and cons either way. You don't have to show the work. You get the answer without showing any work. That's kind of the way of it in a lot of cases with probability. The drawback to that is if there's no work that you can show, then there's no way for me to give you partial credit for the work that you didn't have to show. Right? So these kind of questions tend to be all or nothing in terms of the amount of credit that you would get. Right? So make sure that you're up to snuff on the process and the principles. All right. So on the next page says, is the probability of getting an A given that you're a male the same as the probability of being a male given that you get an A? All right, so we'll look at them one at a time. Basically, it's two problems in one. So let's focus on this part. So we're just looking at the males. Gonna be all these folks here. All right. And then from there, I just want the number of individuals who got A's. All right, so there's my A students. There's the total males, total number of males, 90 out of 288. All right, so 90 out of 288. Now I want to know if that's going to be the same as going the other way, which is to say that if I just focus on the number of individuals, or the individuals, I should say, that got A's, that would be this group here. What would be the probability that I would be, let's say, obtaining a male? It just sounds weird when I say that. Right, so male given A. Again, we're focusing on just the A students. And from that group, we have 90 individuals who got A's and 247 individuals overall. So 247 and 90. Well, these two numbers can't be equivalent to one another. So is probability of A given male the same as probability of male given A? The answer is a resounding no. All right, whether you put it in your calculator or you just kind of reason it out, it's certainly looking like it's not equivalent. All right. Or if you take a number and divide it by another number, like 2 and divide it by 4, I don't think you would expect to get the same value if you took a 2 and divided it by a 5 or a 10 or something like that. Same numerators, different denominators, you're going to get a different fraction, right? But maybe you don't believe, so you pop it in. And this is what you get. Now, I can tell you, I mentioned this before, that in 2005, the outcomes for these problems were much different than they are now. All right. So the decimal values for these numbers were much further apart 10, 15 years ago. But now with more and more data points, it's actually getting closer and closer to being equal. And I got to imagine, even though it probably will never be exactly equal, I'll get to a point maybe 10, 15 years from now where these two fractions are pretty spot on. Okay? Because if there is independence between the two variables, in this case, the letter grade of an A and the gender male, if there's independence, then these two probabilities should be equal to one another, right? So getting there, not quite. Another way to test for independence, and I say recall, kind of like iffy textbook jargon, but it was mentioned like 2 pages ago, kind of in passing, that if 2 events are independent, then the probability of B given A would be equal to the probability of B. What that would mean is that regardless of what came before, that's the A, this is the preceding event. I just don't know. I don't know how I won the 4th grade spelling bee championship at Dutchess County if I can't even spell with confidence preceding. According to Google, that's the correct spelling. It just looks wrong. All right, so preceding event. Probably should have just played it safe and went with prior event. I can spell that one. All right, the preceding event would then have no bearing on the following event. All right, so these two probabilities would be the same, giving us an independent relationship. All right. So what we're looking for is the probability, it's saying use that information to attempt to show that being male and getting a B plus are independent events. So I'd be looking for the probability of being a male and getting, given that I got a B plus, but I'd also be looking for the probability of getting a B plus, given that I'm a male. In both cases, we're looking for equality, not necessarily with each other, but with, in the first situation, the probability of being a male. And in the second situation, the probability of getting a B plus. So I want to know, are these equivalent? They both have to be equivalent to relations in order for it to be a case of independent events. All right. So we have a few different calculations going on here. We'll work on them one at a time. So the first possible scenario would be probability of being a male given that I got a B plus. So I'd focus on just the B pluses. So that's my given. And then from there, I'd look at the probability of getting a male. All right. So that's 59 out of 120. Then I'd want to know, is that the same as the probability of being a male in general? Well, this is the probability of being a male, 288 out of 653. Now, if the first test fails, we don't even move on to the second test, although I am going to move. It's like the empirical rule. I still want to show you how it works, but we actually wouldn't have to, because if it doesn't work one way, then it doesn't matter if it works the other way. All right, so I just do a quick 59 over 120 and 288 over 653. All right, so 0.492 versus 0.441, they're in the same neighborhood, but they're not close enough that we could say that they're virtually equal to one another. So the answer is that they're not equal. So not independent. You could also say that they're dependent, right? But since they're asking us to determine whether or not it's independent, the tendency is to say things like it is independent, or they are independent, versus they are not independent. Right? But if you were to say that they are dependent, that would be the same as saying that they're not independent. Right? I think that's in the realm of common sense, but I figured I would mention it. Right? So just so we have it for our notes, the other possible scenario. So if this ended up being a case where they were virtually the same, like 0.492 versus 0.497, so something so close that you might as well say that they're about the same. Then we would move on and work on it the other way and say that we're only focusing on the males and we want to know the probability of getting a B plus. So we're still working off the same table here. It's 59 out of the total number of males, which is 288. And I need to know if that's the same as just being a male, getting a B plus in general, which would be 120 over 653. All right, so I would just run those numbers, assuming that the first trial worked out. Assuming this worked out, then I would run these numbers and get something. Let's see what it is. hey, see, they're in the same neighborhood. In fact, this is closer than the other set of fractions. So, 0.2 versus 0.184. That's not too far off. So it tells me that, yeah, they're not independent, but maybe they will be with more data. So you don't go through this now and say, because it's sort of like a dangerous weapon that you'll have at your disposal, because people will look at this and say, well, they're not independent. Okay, and follow that through to its logical conclusion. So they're dependent. Maybe not. We haven't really proved that they're dependent on one another. We've just shown that they're not independent, right? You say, well, isn't it one or the other? Well, you got to kind of look at it as not independent, dependent, or inconclusive. The jury's out. We don't have an answer, right? Because you could look at this as a simplistic viewpoint and say, well, they're not independent, therefore they're dependent. Therefore, a person's gender is dependent on their grade, or their grade is dependent on their gender. Well, it sounds horrific when you say it that way. I don't think that's the case. I know it's not the case because I know who I am. However, if you take a simplistic view of this, that's what it might appear like. But if you throw in the uncertain aspect, or the jury's out, that kind of smooths things over a little bit, because it's like, well, it's not independent. So the default, if it's not independent, would not necessarily be that it's dependent. It's just, it could be dependent, or it could be, I don't know. It could be uncertain. We don't know. It could be more information is required. All right. So that's something to keep in mind. Also, another layer to this, because we think about bias in everyday life, whether it's racial bias or gender bias or anything like that, age bias. And it's a question of grade dependent on gender. That sounds like bias to me. Well, there could be lurking variables involved. So what would make, let's say there is a relationship between the grade and the gender, and it is a dependent relationship. And then you start the conversation of, okay, so what variables are at work here that might cause that to happen? And one of them could be bias, teacher bias. He plays favorites. It could be something like that. You can't dismiss that, but it could also be advertisement. I'm moving beyond grades in the course right now, but I suppose it could be a matter of, like, maybe the folks that were sort of recruited for the class, the focus is more on getting females in the class than it is males. Like, who knows? There's other variables that come into play that need to be accounted for, and if they're not, then you're looking at an overly simplistic viewpoint. Right? So just some things to consider, because as we move into we're not quite there, but as we move toward the third unit, we start taking these little lessons that we've been learning throughout the first two units and kind of broadening their scope to apply to larger audiences, if you will. We take small samples and use it to project upon a population. So conditional probability goes a long way towards helping us to understand those relationships. So I'm going to stop the recording